This is the first of 3 videos for Module 1, a pre-algebra review. In this first section, we will look at 3 topics: finding a list of factors for a number, finding the prime factorization for a number, and finding the least common multiple between 2 or more numbers. In every video, before we look at any example problems, we will have to list and explain a few definitions so that you understand what each problem is asking you to find and some of the things you will need to use in order to solve each of those problems. So the first term we are going to define is the term factor or factors. A factor is defined, or factors are defined as numbers that are multiplied to form a product. One quick example we can show: in the statement 2 times 5 equals 10, both 2 and 5 would be referred to as factors. Those are the numbers that are being multiplied. And 10 would be referred to as the product. That is the result of a multiplication problem. So anytime you hear those words, factors and products, that's what it means. And when we talk about factorizations, those are the different multiplication statements that can be used to represent a number. When we look at the different factorizations of 6, we have 1 times 6, which we can clearly find equals 6, and 2 times 3, which again we can clearly find that equals 6. Now there are no other whole number combinations that will give us 6. So this is an exhaustive list. It's completely finished. And this would be the list of factors, what I just circled. 1, 2, 3, and 6 would be a list of factors for 6. A prime number, this is the second definition. A prime number is a natural number that has exactly 2 different factors, 1 and itself. Now a natural number is nothing more than a counting number, 1, 2, 3, 4, and so on. This list of numbers does not include 0 or any negatives. Now if a number is not a prime number, it is considered a composite number. A composite number just has a different way to be multiplied other than 1 and itself. Now at this point you may want to pause the video and copy down this short list of prime numbers that are given. This isn't a complete list, but if you can remember these prime numbers, then you should be able to work every problem later on where prime numbers are involved. Now that we've gone through a few definitions, let's talk about how to find the list of factors of any number. One particular example, let's find the list of factors of 10. We start by taking the square root of the number. So in your calculator, you would type in the square root of 10, and you would find that it's 3.162. The decimal continues forever. We aren't so much concerned with the decimal as we are with the whole number, the number to the left of the decimal, which in this case is 3. We are always going to ignore the decimal for this procedure. Once we've taken the square root, we will divide the number in question, in this case 10, by every whole number between the square root and 1. So every whole number between 3.162 and 1 will be 3, 2, 1. So you see below that we've divided 10 by 3. That gave us a decimal. We divided 10 by 2. That gave us 5. And divided 10 by 1. That gave us 10. Now we do not like decimal products. We don't like decimal quotients in this case. So 3 is not a factor. Neither is 3.333 repeating forever. 10 divided by 2 gave us a whole number, 5. So 2 is a factor, and 5 is a factor. Every time the number we are dividing by, if it gives us a whole number quotient, the number we divided by and the result will be considered factors. Next, we see 10 divided by 1 equals 10. So 1 and 10 are also considered factors. Here, this is an exhaustive list. We are finished. We don't have to consider any other numbers. So the numbers that are circled will constitute the list of factors for 10. 1, 2, 5, and 10. Now when answering questions, they don't have to be in numerical order as I've listed them. You could put 10, 5, 2, and 1, or 1, 5, 2, and 10. As long as every factor is accounted for in the answer, you should be okay. Let's try a few more. So we want to list the factors of 49. going through the same process we just saw. We start by taking the square root. And the square root of 49 is 7. Once we find the square root, we want to divide 49 by every whole number between the square root, 7 in this case, and 1. So we divide 49 by 7, by 6, by 5, by 4, by 3, by 2, and by 1. Now I'm going to make a list just so that we see what happens with every division problem for these numbers. You may decide once you become really good at this that you don't need to make the list. You can just punch these numbers into the calculator, decide what works and what doesn't work. And either way is fine as long as you're getting the correct answer. So we start by dividing 49 by 7, and the answer is 7. So the number we divided by 7, the result 7, those are both factors of 49. Then we take 49 divided by 6. It gives us 8.16. 6 continues forever. That's a decimal answer. We don't like it. So 8.16 and 6, neither of those can be factors. Next, we try 49 divided by 5. That gives us 9.8. So at least it's a terminating decimal. But since we have any decimal of any kind, 9.8 is not a factor. Neither is 5. We continue down the list. 49 divided by 4 is 12.25. So 4 isn't a factor. 49 divided by 3 is a repeating decimal. So 3 is not a factor. 49 divided by 2 gives us another decimal. 2 isn't a factor. And 49 divided by 1 would be 49. So 49 and 1 would be factors of 49. So as we go back through our list, we see that 1, 7, and 49 are all factors of 49. Now, even though I have 7 circled twice, it's the same number. So it only needs to show up once in the list. We don't want any duplicates. Let's try the same thing with 90. Go through the same process. First, we take the square root of 90. And when we do so, the square root of 90, we will find is between 9 and 10. But it's not a nice whole number like the last example. We have 9.4868, blah, 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 it continues forever. Doesn't really matter if we have a decimal or not. We're only concerned with the whole number answer, the whole number to the left of the decimal. So we want to write the list of all whole numbers between the square root, which is 9 and some change, and 1. So we have 9, 8, 7, 6, 5, 4, 3, 2, and 1. Now, just to simplify the process a little bit, I'm not going to write 90 every time. I'm just listing the numbers that I'm dividing 90 by. Let me draw arrows, and I will write down what the result of each of these divisions is as well. Remember, whole numbers are good, decimals are bad, at least in this example. So 90 divided by 9 is 10. 90 divided by 8 is 11.25. Let's go ahead and cross those out. So we have a decimal answer. 90 divided by 7, 12.85, and that will continue forever. 7's no good. 90 divided by 6 is 15. 90 divided by 5 is 18. I'm just using a simple calculator to find these. You could do long division. You could try to do this in your head. No one will know one way or the other if you have the correct answer. You need to make sure this is something you can replicate. And so if you're using a computer to find all of the factors of 90, you're using a really awesome calculator that won't be allowed on your test, I would advise you to figure out how to use your simple calculator to find these factors. And so other than 4, 7, and 8, all of the other divisions gave us whole numbers. And so every number listed, both on the left side and the right side that hasn't been crossed out, will be a factor of 90. Now, I'm not going to rewrite these in a list, but if you had this problem in the homework, we take each of these circled numbers, put a comma in between, and those would be the list of factors for 90. Let's try one more example for the list of factors, just so we can see what might happen in this particular case. Here we take 97. We want to take the square root. Again, grab a simple calculator, because you probably don't know what the square root of 97 is in your head. If you do, you may need to rethink what class you're in. 9.84, and that will continue forever. We are only concerned with the number on the left side of the decimal. So we make a list again: 9, 8, 7, 6, 5, 4, 3, 2, 1. Now every time, and just for the sake of time, I'm not going to write each factor, each quotient once we divide 97 by this list of numbers. When I divide by 9, I get a decimal. The same is true for 8, 7, 6, 5, 4, 3, 2. The only number that will not give us a decimal quotient, a quotient is the result when we divide, is 1. 97 divided by 1 is 97. So the only whole number factors are 1 and 97. If you remember the second definition we saw on the second slide, this would be considered a prime number because the only factors are 1 and itself. And we have found the list of factors for the number 97. Now let's switch gears and let's talk about the prime factorization of a number. The prime factorization is the factorization in which all the factors are prime numbers. Every whole number greater than 1 has exactly one prime factorization. And so while I'm only going to show you one way to find the prime factorization, some of you may know how to go through this process in a bit different way. Each of you, regardless if you do it your own way, my way, if you did it correctly, everyone will have the same answer because every whole number greater than 1 has a unique prime factorization. Let's go straight into an example. Let's find the prime factorization of 63. Now the method that I'm going to use is the factor tree method. Some people make a tower in order to find the prime factors of a number. I like to use the factor tree. Now in order to make a factor tree, we take the number in question, which in this case is 63, and we write it at the top of our tree. We want to take 63 and divide it by prime numbers. Hopefully you copied down that list of prime numbers at the beginning of this video. If not, I'll make a very small list to the side: 2, 3, 5, 7, 11. That should be enough to get through this prime factorization problem. So we take 63 and we start dividing by prime factors until we get a whole number solution. If you take 63 and divide it by 2, you get a decimal. So we go on to the next number, 63 divided by 3, and that works. You get 3 and 21. 63 divided by 3 is 21. So we write each of those factors down beneath 63. We have 2 branches going to each of those numbers. Now, anytime I have a prime number, I'm going to underline that number. 3 is prime, so it is underlined. 21 is not prime. It's a composite number. So we're going to do to 21 what we just did to 63. And that is divide 21 by prime numbers until we have a whole number solution. So we divide by 2. That would give us 10.5, a decimal. We don't like that. We divide by 3, and we see that 21 divided by 3 is 7. 3 is a prime number. If we look at our list, 7 is a prime number. And once we have all prime numbers at the ends of our branches on our factor tree, we are finished. And this is how we write the answer. 63 equals 3 times 3 times 7. That's why it's called a prime factorization. It's a multiplication problem, a multiplication statement, and all of the numbers being multiplied are prime numbers. If you were to multiply 3 times 3 times 7, you would have exactly 63. So this is the prime factorization of 63. Let's try with a larger number, 567. It doesn't matter how large or small the whole number is, we go through the process the exact same way. So we start dividing by prime numbers. We see that 2 doesn't work. We go to 3, and 567 divided by 3 is 189. We try to divide by 3 again. We get 63. We can kind of cheat at this point because we've already done 63. I'm going to underline my prime numbers. 63 is 3 and 21. 21 is 3 and 7. So just like in the last example, we take the number in question, we set it equal to the product, the multiplication of the prime numbers in our factor tree. 3 times 3 times 3 times 3 times 7. And this represents the prime factorization for 567. Now, if you found these factors in a different order, and maybe you had 3 times 7 times 3 times 3 times 3, that's exactly the same, and that's perfectly fine. It doesn't matter the order that the factors are written. I like to put mine in numerical order because I'm quirky like that. But it doesn't matter the order the factors are written as long as the correct number of each factor shows up in the solution. Now let's look at the last concept that will be covered in Module 1, Section 1, and that is the least common multiple. The least common multiple is the smallest positive number that is divisible by all the numbers in the list. And so when you think of multiples of a number, we're multiplying a number by 1, 2, 3, 4, and those are the multiples. So let's look at the multiples of 4. 4 times 1 is 4. 4 times 2 is 8. 4 times 3 is 12, and so on. If I wanted to find the least common multiple of 4 and 6, I would also need to find the multiples of 6. 6 times 1 is 6. 6 times 2 is 12. 6 times 3 is 18, and so on. But when we look in each of these lists, the smallest multiple that 4 and 6 have in common is 12. 4 times 3 is 12. 6 times 2 is 12. Now that is not the only multiple 4 and 6 have in common. We go further along in the list and we see that each list contains 24. That would be a common multiple, but that would not be the least common multiple because 12 is smaller than 24. So the least common multiple, which you will see abbreviated as LCM for these two particular numbers, is 12. Now, while this is a perfectly fine way to find the least common multiple of two numbers, it is highly inefficient. Highly inefficient. And as the numbers get larger, we will see that it's harder to make a list of multiples for each number to find what numbers they have in common. So this is the process we are going to use instead. Step 1, we want to write the prime factorization of each number. We're going to make a factor tree for each number in the least common multiple problem. Step 2, we will write the product containing each different prime factor the greatest number of times that it appears in any one factorization. It may seem like a mouthful now. It makes much more sense once we see it in action. So as we go through the examples, step 2 will make more sense to you. Basically, we're looking for each prime factor the most times it shows up in any factor tree, and we're going to use that to multiply together. And those are the two steps we will use in finding the least common multiple. So let's look at this first example. Find the LCM, least common multiple, of 72 and 60. So remember, the first step of any least common multiple problem is to make a factor tree. Hopefully you have your prime numbers written down by this point. So 72, we start dividing by the smallest prime, 2. We get 2 and 36. 2 is a prime, so I underline it. 36 divided by 2 is 18. 18 divided by 2 is 9. 9 can't be divided by 2, so we go to 3. 9 divided by 3 is 3. Each of those 3's are prime numbers. Now right away, I will write the prime factorization for 72, which is 2 times 2 times 2 times 3 times 3. We repeat the process with the number 60. So we start by making a factor tree of 60 to find the prime factorization. We divide by 2 and we get 30. Still underlining my prime numbers. 30 divided by 2 is 15. 15 can't be divided by 2, so we divide by 3. 15 divided by 3 is 5, and each of those numbers are prime. So the prime factorization of 60 is 2 times 2 times 3 times 5. That's step 1. Now this is step 2, which seemed a little wordy as we looked at the slide. When I look at each factorization, we have 2's, we have 3's, and we have 5's. In the first list, 2 shows up 3 times. In the second list, 2 shows up 2 times. So the greatest number of 2's we have in any given list is 3. The most it shows up in any list is 3 times. So I'm going to write down my LCM equals, I'm going to write down my greatest number of 2's, which came from the factorization of 72. So we're finished with the 2's, all of them. Now look at 3's. The most 3 shows up in the first list is 2. The most it shows up in the second list is 1. So the most I see it in any given list is 2 times. So in my least common multiple list, I write the greatest number of 3's in any list, which is twice. Now I'm finished with all of my 3's. Now I go to 5's. In the first list, I don't have any 5's. In the second list, I have 1 5. So the most that 5 shows up in any given list is 1 time. So in my product, I write 5 1 time. Now, to find the least common multiple, we multiply all of these numbers together. So we take 2 times 2 times 2 times 3 times 3 times 5. And when we do that, we get the number 360. So the smallest number, the smallest multiple that 72 and 60 have in common is 360. And hopefully you can see just by going through this process with these two numbers that we would never want to make a list of multiples to try to find what numbers they have in common. Let's try another example. Find the least common multiple of 11 and 7. So we go through the same 2 steps we did before. We try to make a factor tree for 11 and a factor tree for 7. We have a problem though. Hopefully you recognize these from that initial list of prime numbers. 11 is a prime number and 7 is a prime number. So we can't make a factor tree for either of these numbers. Basically, the factor tree is just itself. 11 equals 11, 7 equals 7. So step 1, while it seems trivial, is finished. The prime factorization of 11 is 11 because 11 is a prime number. The prime factorization of 7 is 7 because 7 is a prime number. So we skip directly to step 2. In each prime factorization, we have 11s and we have 7s. The most 11 shows up in the first list is once. The most 11 shows up in the second list is 0 times. So the greatest number of 11s in any given list is 1. So I'll write that greatest number of 11s in my multiplication problem for the least common multiple. Now I go back and I look at my 7s. The most 7 shows up in the first list is 0 times. No 7s there. The most 7 shows up in the second list is 1 time. So the greatest number of 7s in any given list is 1. I write that into my multiplication problem for the least common multiple. And since those are the only numbers that are represented in the prime factorizations, those are the only numbers that are represented in my least common multiple. So we go ahead and multiply that. 11 times 7 is 77. I'll mention quickly, and you don't have to remember this, but it does make the problem go by much faster if you recognize this. If you want to find the LCM of prime numbers, the only thing you need to do is multiply those prime numbers together. Now make sure that the numbers you have are actually prime numbers before you try to use this trick. If 10 is one of your numbers, if 20 is one of your numbers, those numbers are not prime. And so you can't use this trick for prime numbers with numbers that are not prime numbers. We can also find the least common multiple of 3 numbers. If we wanted to, we could find the least common multiple of 4, 5, 6 numbers, and so on. You shouldn't see any problems where you are asked to find the least common multiple of more than 3. So no matter how many numbers are in our problem, we start off the same exact way, by making factor trees. So we start with 15. 15 can be divided by 3, and the result is 5. 3 and 5 are both prime numbers, so the prime factorization of 15 is 3 times 5. 18 can be divided by 2. The result is 9. 2 is prime, so I underline it. 9 can be divided by 3, and the result is 3. And each of those 3's are prime. So the prime factorization of 18 is 2 times 3 times 3. 54 can be divided by 2. The result is 27. 2 is prime, so I underline. 27 can be divided by 3, and the result is 9. And 9 divided by 3 is 3. So the prime factorization of 54 is 2 times 3 times 3 times 3. Now in each of these prime factorizations, we have 2's, we have 3's, and we have 5's. Just like we have on the previous 2 problems, we're looking for the greatest number of each factor in each list. So I look at my list of factors, my prime factorization for 15. The most number of 2's in its prime factorization is 0. I go to 18. 18 contains 1 2. 54 contains 1 2. So the most that 2 shows up in any given prime factorization is once. So I write down one of the 2's. And now I'm finished with 2's from every prime factorization. Next, I look at 3. 15 has 1 3. 18 has 2 3's. 54 has 3 3's. So the most that 3 shows up in any given prime factorization is 3 times. So I take that greatest number and I put that into my multiplication problem for the least common multiple. And now I'm finished with all of my 3's. When I look at each prime factorization, the first prime factorization has 1 5, 18 has no 5's, 54 has no 5's. So the most 5 shows up in any of the prime factorizations is once. So in the LCM product, it will show up once, and I'm finished with 5. And we see we're finished with all the 2's, all the 3's, all of the 5's, and we multiply these numbers together. So we multiply 2 times 3 times 3 times 3 times 5, and we find that the least common multiple of these 3 numbers is 270. I can guarantee you at this point that if you're making a list of multiples for 3 numbers and you started at 15, you would not want to write that list all the way to 270. This is definitely a better method than just making a list of multiples.